Okay, let's continue our discussion about example 6.4, the time domain reflectometry analysis for line discontinuity. So as the name suggests, this example is used to demonstrate the effect of time domain reflectometry to diagnose discontinuities, unexpected discontinuities that take place on the transmission line. So for this example, the characteristic impedance of the line is 60 ohm, and the total length of the line is 10 meter, with the propagation velocity as 2 times 10 to the 8th. And we know that the right end of the transmission line is terminated with a short. So as a result, the impulse transmitted from the TDR system shall be reflected at the right end, and it is expected to return to the TDR system by what time delay duration. Well, this can be calculated because the velocity is 2 times 10 to the 8th. So every 1 nanosecond, the propagation distance on the line is 20 centimeter. So for 10 meter, it shall take 50 nanoseconds for the signal to propagate from the left to the right and get reflected at the shorter end. So the round trip traveling time, propagation time for this 10 meter length line shall be 2 times 50 nanoseconds. So we expect it to receive a reflected signal from the short termination at the time instant of 100 nanoseconds. However, due to the presence of this shunt resistor not in the middle, 4 meters away from the transmission line, what happens at the junction of the shunt resistor? Now that for the transmission line system, what is the characteristic impedance looking to the right at this position? 60 ohm, right? How about here? 60 ohm as well. And it shall kept as 60 ohm as it goes toward the right-hand side. However, at the interface, at the position with this shunt resistor, what is the impedance look to the right? What is the impedance looks to the right? Well, it observes 60 ohm characteristic impedance of the transmission line and the 120 ohm shunt resistor. So similar to what we have done in circuit theory, the equivalent impedance, equivalent resistance looking to the right with resistor of 100 ohm connected in shunt with another resistor of 60 ohm. What is shunt resistance? What is the equivalent resistance at this configuration? Well, I suppose you can calculate instantly as what? As 40 ohm. Okay, so at this position, when you look to the right, it observes equivalent impedance, which is made by a shunt connection of a 60 ohm and a 120 ohm resistors at this position. And the equivalent input impedance is 40. So how about the reflection coefficient gamma? Okay, what is the first number we should put in here? Well, 40 minus 60 divided by 40 plus 60. So it's, how much is it? Minus 0.2. Okay, minus 0.2. So minus 0.2 is the reflection coefficient looking to the right across the across the shunt connection of the resistor. How about the transmission coefficient? Well, by definition, it's the sum of 1 and gamma, so that should be 0.8. Okay? Oh. How about the reflection coefficient at the right end? That's -1, because it's a short resistor. All right. And here are some additional information that we have discussed on Tuesday. We say the repetition frequency is 10 to the fifth, which provides you a sufficiently long period of 10 microseconds, so that all the energy injected by the pulse generator will dissipate it on the transmission line, because the transmission line comprises not only the shunt resistor but also matching load at the left end. So to proceed for the analysis of this case, of course we can use in a bouncing diagram to do the analysis. To the right is the end result of the bouncing diagram, but let's begin with some initial step. Well, the first initial step, as I already said, is to calculate the reflection coefficient at the discontinuity, and for this case you have two discontinuity. One is at the very right end, that is the short termination. And the other discontinuity is the location with the 120 ohm shunt resistor. So as I already write on the blackboard, you can check out the reflection coefficient, and you get the reflection coefficient as -0.2, and the transmission coefficient is 0.8. Note that an interesting thing about this is, if you're looking from left to right at the interface, the reflection coefficient is -0.2, and the transmission equation is 0.8. How about the reflection coefficient looking from right to left across this discontinuity? Well, if you're looking from left to right, you also observe a shunt connection of a 120 ohm shunt resistor with 60 ohm provided by the transmission line. So the equivalent resistance or equivalent impedance observed from right to left is 40 ohm as well. So the reflection coefficient observed from right to left is the same as the reflection and transmission coefficient observing from left to right, right? Because you have a strong connection in the middle. And to make this discussion a little bit more interesting, let's try change the configuration of the discontinuity. In the original problem, the discontinuity is made by a shunt resistor. Here, if we change the resistor, 120 ohm resistor, as a series resistor placed in the position of 4 meter, what is the transmission? What is the reflection coefficient? What is the transmission coefficient? All right. So to proceed with this problem, let's take a look at the equivalent impedance observing at this point. How many impedances you can observe at this point? You observe a series in resistance of 120 ohm and the characteristic impedance of the transmission line, which is 60. And they are connected in a series fashion. So the overall impedance, the total resistance observed at this position is what? Is 120 in series with 60. So it's 180. Okay? So the So the resistance or the impedance observed at this position is 180. And using the definition of a reflection coefficient, you can easily calculate the reflection coefficient as 0.5. And the corresponding transmission equation, which is 1 plus gamma, is 1.5. How about the reflection coefficient and transmission coefficient looking from right to left? Again, because the discontinuity is made by a series resistance, the impedance looking from right to left is, again, 120 in series with 60. So it also observed 180 ohm impedance. So it will give you the same reflection coefficient and transmission coefficient. Alright, so let's compare these two results. This one is made with shunt resistance to form the discontinuity, and the one to the right is a series resistance that is included in this discontinuity. Because to the left, because the resistor is connected in shunt with the transmission line, so the equivalent impedance is smaller than the characteristic impedance because of the shunt configuration. On the other hand, because of the series configuration, the equivalent impedance, effective impedance, looking at this position is greater than 60 ohm. All right, so you can find that the reflection coefficient for shunt resistors is negative, while the reflection coefficient for series connection is positive. All right, so we can determine or we can estimate that the connecting fraction of the discontinuity of the resistor based on what? Based on the sign of the reflection coefficient. Now, if it is a negative, then the discontinuity is made with a shunt resistor. If the reflection coefficient is positive, then you have a series resistor to make up the discontinuity. All right, so you can, with the knowledge about the reflection and transmission coefficient at the position of discontinuity, you can proceed for the Gaussian diagram analysis. So here, again, the horizontal axis is the position of the transmission, location on the transmission line, and the vertical axis is the time axis. So as the time increases, it goes from top to bottom. So at the very beginning, unit impulse of 1 volt is provided with this TDR system. So here you have 1 volt of the input signal, and the duration of the input signal is 10 milliseconds. Okay, and as you can see here, it takes about 20 milliseconds because 4 meter ohm of the transmission line to reach the first discontinuity. And you have a reflected signal bouncing back. And then the magnitude shall be 1 times the reflection coefficient at this interface, which is minus 0.2. So the reflected signal, the voltage of the reflected signal is minus 0.2. And it takes 20 milliseconds to reach the discontinuity and another 20 seconds to bounce back. So the time that we observe this minus 0.2 signal shall be starting at 40 milliseconds. And because the impulse lasts for 10 milliseconds, so it ends at 15 milliseconds, right? And using the Gaussian diagram, you can continue for the transmission part at the interface based on the calculation of transmission coefficient, which is point A in this case. You have a signal of point A goes to the very right end of the transmission line, which is terminated by a short resistor and terminated with a short, so the reflection coefficient is minus 1 here. So the reflected signal is minus 0.8. All right? And now that, what happens here? Some of the signal get transmitted, but some get reflected. How about the transmitted part? The transmitted part will be minus 0.8 times what? Times the transmission coefficient at this place, which is 0.8 as well, and it becomes minus 0.64. All right? So at the time instant of 100 nanosecond, which accounts for round-trip propagation of this 10 meters long of transmission line, the signal you observed, which is due to the reflection at the very right end, is minus 0.64, appears at the high instance of 100 nanosecond and ends at 110 nanosecond. So if you continue the bouncing diagram, you shall observe that there is a third impulse returns to the left, which is caused by what? Which is caused by this path, the blue line, okay? Transmitted, reflected again, and then transmitted. And of course, you will have the fourth term, fifth terms, sixth terms, and each following terms will add up to reflection. One at this interface, which is minus 0.2, and the other is at this interface, the short termination, which is minus 1. So the product of the additional two reflection is what? Is 0.2. Positive 0.2, because you have minus 0.2 times minus 1. So you have a 0.2 for additional term. So as you can imagine, every higher order term, that is, every term that you keep observe following terms. And those following terms, which are referred to as higher order terms, has experienced more bouncing back and forth. And because the reflection coefficient are smaller than 1 in terms of magnitude, the energy and the magnitude of the signal becomes smaller and smaller. And eventually, we can say all the energy injected by the TDR system as the impulse signal shall eventually dies out. All right? So as you can see here, the signal will keep become smaller and smaller because most of the energy are dissipated in what? In either the shunt resistance of 120 ohms and the match resistance of 60 ohms within the TDR system. All right? So here's the case of bouncing diagram with line discontinuity. Then of course, in real life, if you already know the configuration of the transmission line system, you should be able to find out what should happen on this transmission line system without going into the TDR experiment. So in practice, in actual application, we usually need to deal with a case of unknown discontinuity on the transmission line. So again, we will proceed, for example, 6.4 again. However, in this time, we will reverse the process based on the bouncing diagram or based on the time domain reflectometry result to derive the configuration of the transmission line system, including the location and the discontinuity type and the value of the discontinuity, which can be a shunt resistor or a series resistor, based on the TDR observation, based on the TDR result. So in this case, the only thing we know is the YA is terminated with a short. We know the characteristic impedance is 60 ohm, the overall length of the transmission line is 10 meter, and the propagation velocity is 2 times 10 to the 8th. But we don't know, we know that, okay, there is a discontinuity appears on the transmission line system, otherwise you have observed some anomaly, the line doesn't function normally. We know there is some discontinuity, but we don't know how much is the resistance, and we don't know where it is. What we know is we can perform TDR test and try to estimate the type of discontinuity and the position of the discontinuity according to the result, which is shown on the bottom right, okay? So without the discontinuity, we are expecting to have a reflected signal due to the process of short termination at the very YM, which shall return at a 100 nanosecond, and the magnitude should be -1, not because of the short. However, it's not, it's still arrived at 100 nanosecond, but the magnitude is different, and we have another signal reflected a little bit earlier, which appears at 40 nanosecond, and the magnitude is -0.2. So what can we do to diagnose the system? All right, the first thing is, based on the magnitude, based on the value of the reflected signal, we can estimate the equivalent resistance observed at the discontinuity, say RL, okay, for the discontinuity. So RL minus 60 divided by RL plus 60 equals to -0.2, and we know that RL is 40, all right? And because this number is negative, the reflection coefficient is negative, so it's in shunt configuration, not in a series configuration. If the discontinuity is in series configuration, then what? Then we will have reflection coefficient greater than 0. All right. So so we know that it's in shunt configuration. So you can calculate the shunt resistance using, well, the equation you have with circuit theory. All right. So you can solve the resistance, the shunt resistance, as 120 ohm. Okay. And the other problem that we can solve is, where is the discontinuity? So again, we observe that the time delay, the round-trip time delay, is 40 nanoseconds for the first reflected signal. So the one-way propagation delay is 20 nanoseconds. So use the delay time and the velocity of propagation, which is 2 times 10 to the 8th. We can find out the discontinuity shall appears at 4 meter. All right? Okay, so that shall conclude our discussion about example 6.5. So now let's move on to section 6.4. So far, we have discussed the effect of resistive termination, and we also look into the effect of resistive discontinuity. However, in actual applications, you are not guaranteed to, you may encounter reactive discontinuity or reactive loading, reactive termination. 所以电感性电抗性我们称之为 reactive 的 component 嘛，那个电阻性为 resistive 嘛，所以你还是有机会遇到抗性的负载嘛，reactive the load, or reactive the discontinuity. So Let's consider an inductive termination 一个电感性的负载。所以我们还是用像右图下面所看到的基本的传输线那这里头你也不要看到，为了让这个分析来的简单一点吧所以我们先用定电压源也就是 DC 的电压源，然后你会看到这里头给你什么？给你传输线的特性阻抗 Z0， 传输线的长度 T 你不要现在问我说 T 不是时间吗？为什么他们老是说这是长度？这是什么？这是 propagation delay 啦所以这个 propagation delay 越大，表示那条线越长所以这个大 T 指的其实是传输线的长度。那当然啦，下面标的也有 Z 等于0跟 Z 等于 L 你也可以说传输线的长度是 L。然后我们先假定它是一个电感性的负载所以最右边的话，你画出来是一个只有 L 的电感那讯号源的内电阻是 Z0 那这样做有什么好处？我们前面几个 example 有讨论过了嘛？这样做有什么好处？你的分析会简单一点等于弹回来讯号就被那个 Z0 因为 match 的 load 嘛吸收掉了，所以它不会再反弹所以在左边看到的反射系数的话是0嘛那右边的反射系数这边是这一节里头最重要的一个问题。右边的反射系数是多少？右边的反射系数是多少？大家要想到的事情是什么？你要想到的事情是，这边是一个电感性的负载。我不知道各位在学电力学的时候有没有记不记得电感的口诀，还是电容的口诀？电容的口诀是什么？先通路后开路。那电感呢？先开路后通路所以假如你观察的时间够长的话，电感它一开始是一个类似短路的开路的结构，但是当你的电感结构里头充满能量之后，它的行为又像是一个短路结构那电容就反过来嘛。电容一开始可以充电的时候，它的双板之间有什么？有那个有等效的 displacement current 嘛这个我们是在第几章？第3章的时候讲过嘛displacement current， 所以它一开始在充电的过程当中是可以导通电流的但当它充饱电之后，它的电场没有再变化的话，电容的阻抗就变成什么？就变成无限大所以电容是先短路后开路电感是先开路后短路所以在这边在最右端所看到的反射系数伽马要怎么看？伽马 by definition 是什么 ？V 负 over V 正但这个 V 负是什么？这个 V 负是你那个 low resistor 的电压。可我们刚刚讨论过了嘛 ，V 在电感上面的电压，其实不是电感上面的电压，不是V 负讯号为了满足电感的电压电流关系式所产生的 V 负讯号。所以我们刚刚的讨论，你是不是可以大胆的写下来？它其实是一个 time function。也就是说，这个 V 负的电压值其实会随时间改变的。一开始读开系的时候，它是开路，但是 eventually 它会变成是0。就是因为你那个 VL 的那个讯号是一个 time domain 的讯号所以意思就是说你的 reflection coefficient 也会变成是 a function of time。所以当然还算是 reflection coefficient 吗？从严格意义上来讲，它就不算了。所以对于 reactive 的这个 component 来讲，你大概不能够用 reflection coefficient 是一个常数这样的简单概念来去处理这种电抗性的负载，好不好？好，那接下来我们就来看这一个 inductive termination 的分析了哈。Alright, so let's check out what happens with this inductive terminated transmission line. So again, initially, that is t smaller than 0, the transmission line is uncharged, which means that there is no voltage signal or current signal reside on the transmission line. Only when t is greater than 0, the switch to the left closes on, and what happens next? The DC voltage source shall start to charge up the circuit, should start to provide energy and inject this energy into the transmission line system. All right? And how does it charge up this transmission line? Well, it will provide a voltage signal and current signal as V plus and I plus. So you will have V plus and I plus signal, which suggests they are going from left to right, the forward-going part starting from z equal to 0 from the left end of the transmission line and propagate toward the right, propagate to the right. All right? So what is the number for V plus and I plus signal? Well, we have done that before based on the circuit configuration of the system. You can calculate the V plus and the I plus signal. So here, okay. So because the characteristic impedance of the transmission line is Z sub 0 and the internal resistance of the generator is Z sub 0 as well, so the V plus signal can be calculated as V sub 0 over 2, where V sub 0 is the voltage of the DC source. So the voltage is V plus is V sub 0 over 2. And the corresponding I plus signal, the currents going to the right, can be found as V sub 0 divided by V plus divided by Z sub 0, the characteristic impedance. And because V plus is V sub 0 over 2, so I plus is V sub 0 divided by 2 times Z sub 0. All right? So the relationship is relatively simple. Okay, so you have V plus and I plus signal going to the right, and everything goes smoothly for a short period of time. However, eventually they will reach to the right end, where they will bump into the termination inductor. What the condition? What are the boundary conditions provided by the inductor? So you should look up the voltage and current relationship of an inductor, which can be found in the next slide. That is VL, V sub L, the voltage across the inductor equals to the inductance L times time derivative of current, IL, the current goes through the inductor over time. Okay, so it's a little bit complicated than resistive load. For inductors, V equals to L times time derivative of I. So you need to supply this relationship to the equation above. Well, what we know is when the V plus signal reaches to the right end, it encounters an discontinuity, the inductive termination. And because the boundary condition is changed, so to satisfy the boundary condition defined with the inductor, you shall have a V minus signal and I minus signal, so that the overall voltage over on the inductor shall satisfy the boundary condition. Okay, so the unknown we can make is V minus, the reflected voltage, as well as I minus, the reflected current. Unfortunately, the I minus part, the reflected currents can be written as reflected signal is V minus and I minus equals to the minus of V minus over Z sub 0. Okay, now, so you can substitute I minus with this representation. Okay, so here is, so at this part you have the overall voltage V plus, V minus, and the overall current I plus and I minus, and the two forms the voltage across the inductor and the currents goes into the inductor. So these two terms can be used on the next page, which is the voltage and current relationship of the inductor. So you substitute the total voltage representation and the total current representation. And as you can see here, for the current part, you need to perform a time derivative of the IL signal, the total current, including the I plus part and the I minus part. And to perform time derivative, what can you conclude? What result can you have? Well, in the parentheses, you have two terms. The first term is I plus term, which is V sub 0 over 2 times Z sub 0. Both of them are constants. They are not time variant. So if you take a time derivative over the first term, what is the result? 0, right? Because they are DC signal, right? They are not time dependent. So the only thing that we can get from this time derivative operation is the second part. So the equation can be somewhat simplified as this, okay? And in this equation 6.52, we do a little bit massage on this equation. So you have L over Z sub 0 times the first order time derivative of the V minus signal plus V minus, which is first order term. Or you can say that zeroth order term in terms of time derivative. And equals to minus V sub 0 over 2. This is constant. This is a constant. So overall speaking, what can we observe from equation 6.52? It's a first order partial differential equation， 一次偏微分方程式。所以6.52满足一次偏微分方程式的格式。所以我们会做的是什么？找出一次偏微分方程式的一般解形式，然后代入所谓的边界条件或者是初始条件，帮我们找出一般解的方程、一般解的那些常数的值，然后你就可以得到所谓的 specific solution 特定解，好不好？所以我们就要解的是把这一个 V 负讯号的 first order differential equation 带入 initial condition 初始条件来去解出这个 V 负会长什么样的一个形式。那当然你可以猜得到的时候，它应该是一个 time dependent 的 function 是会跟时间有关的一个函数，有没有？So the initial condition is that the current through the inductor is 0 at the time instance of t equals to capital T. That is the very moment that the V plus signal reaches to the Ym. And we know that for an uncharged inductor, the initial voltage or the condition of this uncharged inductor can be equivalent to what? To an open circuit. So we can use the reflection coefficient of open circuit. Now that is only valid at the very time instant of t equals to capital T. So at this very moment, the inductor is uncharged, so it behaves like open. So the reflection coefficient here is 1. Alright? Which means the reflected signal V minus shall be the same as the incident signal V plus. That is V sub 0 over 2. Alright, so here is our initial condition. And based on the V minus description, you can write up the I minus current as well. But, well. Alright. So here is the first order differential equation. And the general solution for first order differential equation is what? It's an exponential function. Alright, so it should be in the form of exponential. With this part as what? As the so-called time constant of the circuit, as what we have done in circuit theory. So note that the time constant for inductor is what? Is L over R. How about the time constant? Tau means time constant 不好意思，那个 Greek letter 就是那个20来个然后大小写算起来40个在科学领域里头一下就用光光了所以有一些重复用。所以这个 tau L 指的是电感所看到的 time constant 所以还记得吗？电力学里头电感的 time constant 是多少？ L over R。那电容呢？RC 嘛，那个 R 电容的话 R 是乘在上面，电感的话 R 是在下面。好，所以对于这一个 case 来讲，那个电感，那个 R 是什么？也就是你在接电感的时候，它所看到的等效电阻。所以这一个电感，它能够看到的电阻是往哪边看？往左边看过去嘛，所以它看到的是什么？看到的是 Z0 Z0 是往左边看过去传输线的 characteristic impedance 嘛，所以把这个结果带进去，它的 time constant 就是 Z0 over L 所以那个地方其实是什么？它的一般解的形式是 exponential minus t over tau 这是那个还有一个 a 啦，这边还有一个 a。这个是一阶偏微分方程式的一般解形式，所以我们要想办法找出这个 a， 这是我们的未知数。tau 呢可以从刚刚的那个分析里头，电路的分析里头找出 time constant， 所以这是 tau 分之一啦，所以你本来的 time constant 是 L over Z0，所以转起来变成是 Z0 over L，导数。Z0 over L， 然后前面的那个负2分之 V0 呢，是为了要凑出那一个特定解所得到的结果我们来验证一下就 6.54 的那个式子。6.54的这个式子它其实是有效期限的。它的有效期限是什么？它的有效期限是 t 大于大 T 啦，也就是你的 V 正的讯号跑到最右边打到这个电感上面的时候，它开始产生 V 负讯号的时候才是它的有效期限所以你会看到 6.65 的 V 负讯号的表示是在 6.67 的57的6.56和 6.57 的电流的表示是它的标上有效期限就是 T 大于大 T， 好不好？然后我们把 哦，我们刚刚还没有把 A 算出来哦，对不对？啊，我们只找到那个什么 V 负讯号的一般解形式。啊，用我们所已知的资讯，在上页里头你找到的其实只是它的一般解形式 6.54， 但是这里还有一个未知数 A。啊，所以怎么找到 A？ 就是把已知的条件带进去啊，也就是我们的 initial condition。我们知道在 t 等于 capital T 的时候，你的 V 负讯号必须是 V0/2。为什么？因为这个时候的电感的特性就像是一个开路啊，就像是一个开路。所以我们把时间用 t 等于 capital T 带进去啊。你们看到原本式子里头这个是小 t 哦，啊，但现在变成是大 T。OK， 然后呢，把其他已知的东西带进去哈，这是 V 正讯号，这是 initial 的 V 负讯号啊，然后大 T 带进去，所以这个拿过去变成是一个 V0啊，那所以整理一下，你可以得到 A 等于 V0乘上 exponential Z0/L 乘上大 T。然后再把这个 A 带回去前面 6.54 的表示式，你得到这一个结果，可以吗？那因为 A 本身就是一个 exponential 哈 ，exponential 的讯号，然后后面还有一个 exponential， 注意在这边，这边还有一个减小 t 嘛哈，那这个是一个大 T， 所以整理一下就变成是负的 1/tau， 也就是 time constant 导数乘上小 t 减 t 啊，那这个小 t 减 t 其实也代表什么？也就代表这一个 V 负讯号的表示式是在超过大 T 的时间才有效的。好，所以我们再看一下 6.56 的这个式子，这个式子里头有另外几个点我提醒一下 ，V 负这边写作小括弧 LT 这三位数。T 是时间啦，但是这个 T 的小 t 的时间要在大 T 以上，超过大 T 才有效。这个表示什么？表示这一个 V 负的电压只有在 Z 等于 L， 也就是最右端才是对的其他地方呢不一定是这一个其他地方的话，这一个在其他的位置这个答案是会有可能有所变化的好，所以它会是这样子的一个情形。然后，假如要纠察验证是否错误的话，我们把小 t 用大 T 带进去，好不好？假如用大 T 带进去的话，这边等于0，那 exponential minus 0等于多少？等于1嘛 ，OK？ 所以假如 exponential 这个部分在 t 等于大 T 的时候，也就 exponential 等于1，那你这一个 V 负讯号等于多少？等于 V 负1/2 V0 加上正的一个 V0， 所以等于正的1/2 V0， 跟我们原先在看的 initial condition 的电压 V 负的一开始的电压是1/2 V0 是一致的。OK， 好，所以这是 initially 的时候，你的 V 负讯号在 t 等于大 T 的时候是1/2 V0。那么再做一个检查。这个时候我们要检查什么时候？你猜嘞？你猜我们应该检查什么时候？我们可以猜很久以后，好不好？也就是说这个小 t 的时间够久，够久的时候为什么说够久？因为够久你知道那个电感会变成什么？短路嘛，对不对？那个时间很刚接上的时候，那个电感像是开路，但只要你时间够久，它就会变成短路所以我们假设时间够久是 t， 你的 lowercase t approaches to infinity what happens with B minus signal? So if lowercase t approaches infinity, this will be a negative, relatively a negative number, a large negative number. No, I'm sorry. A large positive number however, because of the minus sign, it will becomes a very small number for this exponential part. Okay? Because when t is much greater than capital T, this thing becomes a number approaches to 0. Approaches to 0. Then V sub 0 times 0 equals to 0. So what happens about V minus at a sufficient, after a sufficiently long time? Well, it becomes minus V sub 0 over 2. And how about the relationship of V minus signal and V plus signal? The V plus signal is V sub 0 over 2. And using this equation with sufficiently long lowercase t, it approaches to minus V sub 0 over 2. So what is the ratio of V minus over V plus? It equals to minus 1. So again, it confirms that for an inductor, the voltage relationship, the inductor with a sufficient, when the inductor is charged up, its condition becomes approximate to a short circuit. All right, and we found that the V minus voltage over V plus voltage also approaches to minus 1, which again confirms the condition of a short circuit. However, before we end our discussion about this example, I shall note again that here are the expression for V minus signal and I minus signal. Again, you see they are both function of time. So strictly speaking, the idea, the concept of reflection coefficient is not applicable for time domain analysis with reactive elements. All right, because the ratios in terms of voltage and currents are not constant number. They are function of time. All right? So here are the total voltage on the inductor. So here is the total voltage on the inductor, which is the sum of V plus signal and V minus signal. So again, it can be seen as this. It's obeys the relationship of inductor. Okay, so here's the voltage relationship. This is the current representation, and the more interesting part is the graph. All right. Again, I have told you that I'm particularly fond of graphs. All right. So here is the time domain response of the voltage signal across the inductor. Now, so you can see that the time instant of capital T, it reaches the V plus system comes in, the V minus signal is the same as the V plus signal. So the total voltage across the inductor is V sub 0, and eventually it will die out as a short circuit. And here's one condition that I need to remind you of is this is the idea for the so-called time constant, which means this is the time required for the signal across the inductor to somehow saturate. If you substitute this time instant into this relationship, you found the voltage here is V sub 0, that is the initial voltage across the inductor, times exponential of minus 1, which is what? 0.36a, or to remember that easier, it's about 1/3. Okay, so that is the voltage signal is saturated to about 1/3 of its final result is the so-called the time constant. All right, so here you can refresh your definition about the time constant. This is the time required for the signal to stabilize, to saturate, to stabilize to about 1/3 of the between the initial condition and the final condition. And you can also see that based on the current graph, the currents as the inductor is charged up, the current becomes larger and larger, and it can be approximated as an open circuit at the beginning and short circuit with a sufficiently long time. All right. So so I think I already discussed that at the steady state, that is, with a sufficiently long observation, the inductor will eventually becomes a short circuit, Okay. As we already know from circuit theory. All right, so let's break for 5 minutes.